Welcome to the world of linear algebra, the world of matrices. Today we will be exploring cofactor expansion to find the determinant. A determinant is a number associated with a square matrix that helps us to find many other terms in linear algebra, including inverse matrices and solutions to a system of linear equations. Cofactors are essentially determinants of smaller matrices located inside the main matrix to help find the determinant of the main matrix. This helps eliminate the need for longer algorithms that take long to compute. These formulas show two different versions of the cofactor expansion, one in row expansion and one in column expansion. The formula for row expansion takes the cofactor expansion along the row I, and the column formula takes the cofactor expansion along column J. Ideally, the row or column expansion should have the most zeros, because if you look at the row or column expansion formula, the matrix elements of 0 would substitute here, 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 and here, and would cancel out with the cofactors, and the overall element would be 0, thus making this sum easier to compute. Now the cofactor is composed of two elements, the sign associated with the cofactor and the magnitude of the cofactor, which is the determinant of the smaller matrix that results when the row and column of the cofactor are cancelled out of the larger matrix.
Okay, let's look at our first example here. Find the determinant of the matrix using cofactor expansion down column 2. Let's use the column formula that we learned earlier. Substituting values of column 2, we get the determinant of A equals 0 times the cofactor of 1, 2 minus 1 times the cofactor of 2, 2 plus 6 times the cofactor of 3, 2 plus 8 times the cofactor of 4, 2. Notice first how we could eliminate cofactor 1, 2 because of its 0 coefficient. This is a neat trick to calculate the determinant quickly by finding a row or column where some of the entries are 0. In this case, we could have used column 4 or row 1 to solve it quickly, but we're going to use column 2 to illustrate it. Now, it's time to evaluate the actual cofactors. Using the cofactor formula, let's look at cofactor 2, 2. Notice how the sign multiplier is chosen to be 1 or negative 1 based upon the entries located in the matrix, its I and J components. This is a key place where students mess up, so make sure to pay attention to this. Now let's look at the determinant of this new matrix. This matrix was created by covering up the row and column associated with the entry we're dealing with. So since we're dealing with entry 2, 2, cover this row here, or this column here, and this row here, we get a new matrix, 4, 0, 0, 2, 3, 0, and 5, 4, negative 3. We can calculate the determinant of this new 3 by 3 matrix by using more cofactors or by using the diagonal trick. When we calculate it, we get the answer of negative 36. But make sure you remember to multiply by the sign multiplier, which turns out to be negative 1 to the 4th power, which is just 1. Next, let's go to cofactor 3, 2. This same process applies to this new entry of 3, 2 here. We cover up the column here and the row here and create a new matrix 4, 0, 0, 7, 0, 0, 5, 4, negative 3. Evaluating the determinant of this one, we get 0, and when we multiply the sign multiplier, we still get 0. Finally, evaluating the last matrix, we get another determinant of 0 for our 3 by 3, and we can finally find the determinant of our matrix A by using the determinant formula we learned from before and multiplying by constants. So 0 times 0 minus 1 times negative 36 plus 6 times 0 plus 8 times 0 all gives us an answer to 36.
Now let's look at the second example. In this example, we are going to solve for the determinant of this 4 by 4 matrix. We are going to use the second column to solve for a determinant. We encourage you to pause this video and try to solve this problem first, and then check with our solution. Now, after we solve this example, let's look at the solution. First, this is the equation we're going to use. The leading coefficient in this equation, 2, 0, -2, and 1 are all from the second column. And then it's 2 multiplied the cofactor of 1, 2, plus 0 multiplied the cofactor of 2, 2, plus -2 times the cofactor of 3, 2, plus 1 times the cofactor of 4, 2. Now, after look at the equation, we're going to look at each cofactor. This is cofactor number 1, the cofactor 1, 2. To solve for this, we're going to use -1 raised to the power of I plus j, which is 1 plus 2 in this case, times the determinant of this 3x3 matrix after we get column 2, row 1 out of the way. In this case, it will be -1 times to the determinant of the 3x3 matrix, which is -1, it gives you 1. In the second cofactor matrix, since the leading coefficient here is 0, so we do not need to calculate it, it's gonna give you a 0 automatically. In third cofactor matrix, we do the same thing first, which is -1 raised to I plus j power, which is 3 plus 2 in this case, times the determinant of the 3x3 matrix. In this case, it will be -4, so it will be -1 times -4, that gives you 4. Now, let's look at our last cofactor. Same thing first, -1 raised to the I plus j, in this case 4 plus 2, times the determinant of the 3x3 matrix. In this case, the determinant is 6, so it will be 1 times 6, that gives you 6. Now, let's sum everything up. Here is the last step. Determinant A is equals to 2 times 1 plus 0 plus -2 times 4 plus 6. And then this should give you 0. If you get this one, you are so good. This one's a trumpet, right?
Middle school band memories.
The saxophone now.
Sounds like a dying duck.
You died in the last part.